Routing principle. Before we understand three main steps in IP routing, that is finding out longest matching route and exit interface, switching, that is moving packets between the interfaces, and encapsulation, that is step number 3, building layer 2 header. But before we understand like all three steps in detail, let me quickly take one scenario wherein there are two routers, R1 and R2. Both routers are connected and host 1 device is connected to LAN segment of R1, and there is another host device, that is host 2, connected to R2. IPs are properly configured on both the routers, right? Even routing is also configured. Host 1 IP, gateway, all configured, pre-configured. But still there is end-to-end IP reachability issue. So whenever we try to reach out to host 2 from host 1, or maybe from host 2 to host 1, then there is issue. In fact, there is no connectivity at all, right? So we are going to see like what's the problem, like why there is reachability issue, right? Why like both host devices are unable to communicate with each other, and we would apply routing principle or routing knowledge to fix that issue, right? So let me quickly show you like topology, configuration of both the routers, and what problem exactly we are facing, and then I'll be back to 3 steps of routing, right? We'll understand all 3 steps in detail and we'll apply the knowledge, skill in fixing routing issue, right? Because I know like you all know like what is static routing, what is dynamic routing, how to create static routes. That's not very complex, right? But understanding 3 main steps in IP routing is really very important. Okay. So if you look at topology here, then there are 2 routers, R1 and R2. Interfaces like configured with IPs 10.0.0.1, 12.0.0.1 and 12.0.0.2, 172.16.0.1. Host 1 IP is 10.0.0.2, host 2 IP is 172.16.0.2. So what I'm going to do first, I'm going to initiate ping from host 1 to host 2, and let's see what error message we get here, right? Whether RTO or some destination host unreachable, or reply from gateway address and then destination host unreachable, right? And then we will open CLI console of both the routers R1 and R2. We'll try to investigate, we'll try to figure out the problem, right? And if we have been successful to know the problem, to identify the issue, then of course like we can fix that issue, right? And then in the same context, I will explain routing principle, all 3 main steps in IP routing, right? So let me open host 1. So host 1 device, and let me quickly check the IP address configured here. So IP address is 10.0.0.2 and 10.0.0.1 is the gateway address, correct? IP and gateway both are configured. Alright, so let me ping host 2 device. Host 2 device is behind R2, right? 172.16.0.2 is host 2 behind R2, okay? But there is an error message, request timed out, RTO, nothing like destination host unreachable, or reply from gateway address and then destination host unreachable. So now what I'm going to do, I'm going to ping gateway, that is 10.0.0.1, just to check like IP reachability between host and the gateway device. So there is proper IP reachability, so I can ping R1, that is gateway 10.0.0.1, right? So there is IP reachability from here to here, so there is no issue at all. Okay, so R1 console, here we have R1 router, IP int brief. So IP is configured, interface up, 12.0.0.1 interface is up. So can we ping from here? Can we ping destination, that is 172.16.0.2 from R1? So no, it's not reachable from here also, right? Ping 172.16.0.2, success rate 0%. What about the routing table? So it has like route here 172.16.0.2 and exit interface is F0/1. So if you look at topology here, so in order to reach 172 network, exit interface should be F0/1. Looks good, right? So this way there should be proper communication, but no. And can we check external interface IP, I mean 12.0.0.2, just to ensure like reachability between both the routers? Yes, both the routers are very well connected, right? And even there is no need to check the routing table of R2, because if we are pinging from here from R1, right? So by default, exit interface IP means source IP address would be 12.0.0.1, right? Because whenever we ping from the router itself, like 172.16.0.2, so source address 12.0.0.1 and destination would be 02. So even if R2 doesn't have route for 10 network, there is no problem. There shouldn't be any problem, right? Why? Because 12.0.0.1, 12.0.0.2 directly connected network segment, right? They both like have IPs from the same network, right? So R2 definitely would have route for 12.0.0.1 also, being the directly connected interface. Okay, so even if we cannot ping from R1, so of course like there's some other issue. It's not like something related with the R2 routing table, right? But why like there is no communication? So segment between R1 and R2, yes, like there is proper IP reachability, host 1 to R1, yes, IP reachability is there. Even if we check the R2 interface here, show IP int brief interface, like yes, up. What about routing table? There is route even for 10 network. Exit interface is correct, F0/1, F0/1, right? Now let's understand now routing principle in detail, right? And then we would do the further investigation, and once problem is identified, then we will fix that. You understand the objective, right? The whole objective. So what is routing principle? So in routing principle means total there are 3 main steps in IP routing. 3 main steps, right? Step number 1, finding out longest matching route, and then second part is finding out exit interface. Means in step number 1 there are 2 parts. First, finding out longest matching route. So what do we mean by longest matching route? So let's understand first point and then second one, exit interface. Both are important, right? So finding out longest matching route means if R1 has route to major network address /16, also subnet address maybe /24, default route 000, right? Maybe 172.0.0.0/8, and also a specific route 0.2, for example /32, right? Multiple routes in the routing table. So what happens when R1 would perform routing table lookup, right? Longest matching route will be preferred. So longest matching route means here host route, right? So which route will be preferred? This one, because in routing table sequence is not very important here. It's not firewall security policy or access control list, right? Entire routing table is checked, right? Concept here is longest matching route. So if there is a host route, all 32 bits like matching, then yes, host route will be preferred. In case if there is no host route here, then the next best available path would be subnet route. Subnet, right? And if like there are multiple subnets, so larger subnets may be subnets if aggregated. Network, if networks are aggregated, like here we have /8 or something, then that network like supernet, subnet, right? And then finally default route. So path selection or routing table lookup is done based on longest matching route, like how many bits of destination IP exactly match with the route. That's first step, right? So in this case, if like we are trying to communicate with the host IP 172.16.0.2, then definitely this route will be used here, longest matching route. In longest matching route, and let me clarify another important point here, because a lot of like I've seen engineers like very much confused with this concept, longest matching route, and also with the AD value and metric. That's something different, right? For example, if there are two different routes to reach the destination, maybe destination is here, R4, R3 via R2, right? Destination is 40.0.0.0/8. So if there are two different ways to reach to the destination, that is 40.0.0.0, right? So which route will be installed in the routing table, that is determined first on the basis of AD value. Lowest AD value is preferred, and in case if there is tie, right, same AD value, then metric. And metric could be like in case of OSPF, cost, or RIP means hop count, ESRP, then composite metric, right? And if again there is tie, then equal cost, multipath, or load balancing is done. So which route will be installed in the routing table is determined with AD value, metric, or cost, right? But if already routes are installed in the routing table, so at the time of making routing decision, which route will be used, preferred, that is determined with this concept, longest matching route, right? Both are different. So I hope now you understand like the first part of it, longest matching route. What about the next one? Exit interface, finding out exit interface. So let us assume like R1 has routing information, I mean 172.16.0.2 is the maybe static route, right? And here there is next hop IP configured in routing, and next hop IP is 1.1.1.2, for example. So what happens here? Next hop IP address is known, but not the exit interface. So now if R1 has multiple interfaces, right? Maybe F0/1, F0/2, Gig0/1, and LAN segment is F0/0. So since there are multiple exit interfaces, right? So it becomes really very important to like find out exit interface, which interface should be exit interface, because it's okay, like there is a matching route here in the routing table, that's fine, right? But next hop IP address is also mentioned, but in order to reach 1.1.2, which exit interface would be used, because there are multiple interfaces, right? And this concept is really very important in firewalls also, and you must have seen in Palo Alto firewall, in FortiGate firewall, even routing is done before like matching traffic with any policy. And why it is so? Because in order to determine destination zone, right, routing table lookup, or maybe to just get the exit interface, routing table lookup is done prior of matching packet with any policy. So what happens here? Next hop IP is 1.1.2. So now routing table lookup will be done again, like how to reach 1.1.2, right? So if let's say 1.1.1.0 is directly connected with the F0/1 interface, is a connected route represented with C, then yes, recursion is finished now. And that's what recursion is, reverse routing table lookup, recursion to know, like to get the exit interface. So when exit interface is known, then yes, we can jump to the step number 2, right? And you must have seen like in like OSPF or maybe RIP protocol or EIGRP, whenever we look at the routing table, let me show you. Whenever we look at the routing table, then here like we find both. In the routing table here, we find both like IP address, exit next hop IP address with exit interface, right? And best way of doing routing, wherein next hop IP and exit interface both are known. So there is no need of doing recursion. Reverse routing table lookup not required really. But in case of static routing and BGP, border gateway protocol, next hop reachability issue may arise, right? You can look at this routing table. However, there is exit interface directly here. So even recursion not required here again, because in routing itself, next hop IP address is mentioned. Exit interface is mentioned here, not next hop IP address. So even recursion is skipped now. So is this the best way of creating a static route, like with the exit interface? Because here there is no next hop IP address. So I will come to that point. Just hang in there. So first point, I hope you understand. Like, so first point is finding our longest matching route and then exit interface, right? So if exit interface is not known, then multiple routing table lookup is done, like recursion or reverse routing table lookup, right? So if next hop IP is maybe 4.5.6.7.8, so now router will check the routing table. How do I reach 4, 5, 6, 7, 8? So let's say the next lookup, then in order to reach 4, 5, 6, 7, 8, next hop IP address should be 1, 2, 3, 4. Then again one more time recursion will be done. How to reach 1, 2, 3, 4, right? So reverse routing table lookup or recursion will be keep on like happening till like exit interface is determined. And sometime in GRE tunnel or something with improper configuration, even this may create a loop like that, something in order to reach 1.1.1 exit interface would be tunnel interface, and tunnel interface means like 1.1.1. So this is something like, you know, like it creates problems. So let's not get into that for now. We maybe will understand in some time else, right? So I hope first point is clear, finding out longest matching route and exit interface, right? What about the second step? So now ingress interface here, F0/0, right? Ingress interface, ingress. So how like this ping packet will be sent to R1. So ping packet means IP, ICMP encapsulated further, and here like layer 2 header, that is source MAC and destination MAC. So destination MAC would be R1 MAC address, gateway MAC address, and source you understand, and here for the error checking, frame check sequence, right? So what R1 does, R1 after performing error checking like CRC, running CRC, like layer 2 header is removed, and of course FCS is removed, packet is extracted from the like this frame, and IP header means like source IP, destination IP, right? So R1 performs routing table lookup, all done. Let us assume all done properly, there is no issue, right? So exit interface is determined now. Okay, so what happens now, packet like is moved, which is known as switching between both interfaces, right? So now packet goes to exit interface, and exit interface here is F0/1. So what happens here, packet is moved. Packet means IP header and ICMP, no layer 2 header in it, right? And frame arrives here. Frame means like with layer 2 header and frame check sequence, both are removed. Packet like switching done here, and now this is time to send packet to the R2 next hop device. So what happens here? Packet is sent? No. Again, this packet means IP and ICMP is further encapsulated. Step number 3 here, right? Encapsulation, building layer 2 header. So again, layer 2 header is added to the packet. That becomes frame. This portion is known as data frame and this portion is packet. So layer 2 header is added and maybe like some error checking technique. So in case of Ethernet media, if this media is Ethernet, then again source MAC and destination MAC both will be added here inside layer 2 header apart from ether type field. So now here comes like the step number 3. So what happens here? Let me now go to this page. So step number 3, we have reached to step number 3, encapsulation. So what happens here? R1 now sends ARP broadcast message asking who is 172.16.0.2. Tell your MAC. Now question here. Why R1 is sending ARP request to obtain MAC address of end host device destination? Why not next hop IP address? Right? Because if you look at the routing table here, R1, right? Let me show you. Show IP route. So if you look at the routing table here, and okay, so there is a route for 172 network and directly connected to F0/1 interface. So what R1 assumes? R1 assumes as if destination means any host from this network is directly connected to this interface. Directly connected, right? So directly connected means now R1 like assume host 2 means 172.16.0.2 is directly connected or directly reachable to this via this interface, right? And that's the reason R1 sends ARP broadcast to obtain MAC address of 172.16.0.2, right? And without knowing the MAC address, step number 1 done, step number 2 done, but what about the step number 3? Not done yet, right? Packet is still not encapsulated, and without encapsulation, packet cannot be sent to the next hop device. So in order to do so, packet is put inside the buffer, right? Exit interface buffer, and R1 is like trying to obtain MAC address of host 2. And now what happens? Host 2 is of course not directly connected on different network segment, right? Host 2 is on different network segment. Here is different network segment. So our broadcast will never be forwarded to different network segments. You understand, like broadcast messages are never forwarded by any layer 3 device in general, right? Means R2 if is not forwarding our broadcast to host 2 means like R1 wouldn't get MAC address of host 2. But what happens? There is concept here, proxy ARP. So proxy means like acting on behalf of other, right? Proxy. So proxy ARP means now R2, if proxy ARP is enabled, then R2 may respond with its external interface MAC address as a ARP reply message, right? So R2 will reply to the ARP broadcast message, ARP reply, telling R1 that MAC address of 172.16.0.2 is like maybe whatever MAC address would be of F0/1. Means R2 now responding to ARP requests or broadcast messages on the behalf of connected host. So basically R1 will obtain MAC address of 172.16.0.2, but definitely that wouldn't be of 172.16.0.2, right? 12.0.0.2 IP or F0/1 interface. So what happens now? R1 obtains MAC address, then R1 will perform like do encapsulation, like building layer 2 header, now packet is further encapsulated, right? Sender MAC, destination MAC. So destination MAC would be of F0/1 interface. So packet is sent to R2. R2 will again like remove external or outermost layer 2 header, will look at the IP header, will find destination IP 172.16.0.2. R1 will send R broadcast again, who is 172.16.0.2. Tell your MAC host 2 will just provide the MAC address. Packet is again encapsulated and forwarded to host 2, right? Now here there is a catch. If proxy ARP is not working, proxy ARP is not enabled, right? Then what would happen? Of course, there will be issue at step number 3. Routing table lookup done, exit interface yes determined, switching is done, it's internal process, moving packets between the interfaces. Where is problem? At step number 3. Because what we understand routing all about is just like if there is proper route in the routing table, there is proper like WAN connectivity interfaces are like there is proper interconnection between both the devices, then that's done. No, like we would have to take care of all the 3 steps, because a lot of time what happens, even router finds matching route, then maybe issue with in determining exit interface, right? Recursion. So you like router may get stuck in determining exit interface, right? Maybe can get trapped in any loop, right? And this mainly happens with improper configuration in GRE tunnel or any other tunnel configuration. So now let's do some investigation here and how we can do. So let me enable debug and first like logging buffer, because logging console is disabled, and here I'm going to run debug IP packet detail, right? But in production network you should never run the command like this. In production network what we do generally, we create ACL like this 102 or something, permit IP or ICMP, and then the source IP address, right? Or maybe if we permit ICMP source any, destination any, and then whenever we run the command debug IP packet detail, then we mention here ACL number, right? So you can call the ACL number with the debug command, and that's what conditional debug is, right? But it's a lab environment, so no problem, no worries. So debug is enabled and enabled or not, let me debug IP packet detail, logging buffered. I think already logging console is disabled. So is there any log message? No. And now I'm going to ping again 172.16.0.2 sourcing with my LAN IP and repeat count 2 is more than enough, right? Just we are trying to figure out like what's the issue. So now I can see here like source 10.0.0.1, destination 172.16.0.2 and sending ICMP type 8 code 0, that is echo request packet, and look at the error message here, encapsulation failed. Understood? Encapsulation failed, right? Encapsulation failed. Where is the problem? Step number 1, all good. Step number 2, good. What about step number 3? Here is the issue. Step number 3, right? Encapsulation failed. So as I mentioned before, packet is further encapsulated, layer 2 header is added, and in case of Ethernet media, layer 2 address means MAC address, right? That depends like what interface type we have used. But in case of Ethernet, source and destination MAC address. Destination MAC address, of course, is unable to find out destination MAC address, and that's why encapsulation failed. I can see here. And let me turn off debug. What about ARP message? Show ARP. So we don't see here MAC address, right? So that's the problem. That means either now there are multiple ways to fix the problem. The best way is what? Best way is just changing the route here, right? And just like replacing exit interface with the next hop IP address. So we can do routing this way. Static route this network, and next hop IP what 12.0.0.2. It is one way, right? So what will happen now? R1 will find the matching route here, exit next hop IP this. Then R1 will perform recursion, one more time routing table lookup, how to get 12.0.0.2. So now R1 knows, like, in order to reach 12.0.0.2, my exit interface should be F0/1. So if next hop IP is 12.0.0.2 here in the routing table, then what happens? R1 will send ARP request to obtain MAC address of next hop IP, not the destination, right? This one. So of course there is no problem whatsoever. R2 will respond to our broadcast message. So if we change the routing, we replace the exit interface with the next hop IP address, then yes, there is one issue here. An issue is what? Recursion, reverse routing table lookup, checking routing table 2 times, right? First, like, to find out matching route, and then next time to get the exit interface. But there is another method, and that is what? If we could mention both exit interface and next hop IP, means next hop IP plus exit interface, both. So recursion no more required, because in first lookup even R1 will find next hop IP, exit interface, both. So will that be possible in static routing? Yes, of course that is possible, right? So in BGP protocol, border gateway protocol, of course, like they're like next hop IP not necessarily always connected device, in fact, right? Next hop IP could be multi hops or 3 or 4 routers away. So there, of course, we next hop IP reachability, like finding out route for next hop IP address becomes mandatory. But in static routing, yes, we have the command, we can specify both next hop IP and exit interface. So it is one way, right? To fix the problem, we can change the routing, or we can verify, we can check whether proxy ARP is enabled or not. If proxy ARP is not enabled here, then yes, like, there is a problem, because in case if proxy ARP is enabled, then we understand R1 will send our broadcast message to obtain the MAC address of destination host device instead of next hop IP. But if proxy ARP is enabled, so proxy means like responding on behalf of connected host device, acting on behalf of others. So what would happen? R2 will reply with his own MAC address, right? On the basis of, on the behalf of destination host device. So at least encapsulation will not fail, and there will be success, right? So I've typed show IP interface F0/1 and see here proxy ARP is disabled, and that's the reason. So can we enable proxy ARP? Will fix the problem? Yes. IP proxy ARP done, right? Now let me initiate ping from here again one more time. 2 packet, maybe first RTO one more time. And what about R1? R1 and also I believe proxy ARP is not enabled. Unintentionally I disabled proxy ARP basically, right? Just to show you. Otherwise in Cisco routers by default proxy ARP is enabled, right? By default proxy ARP is enabled. Now you can see here proper response, and if you look at the ARP table, then yes, like 172.16.0.2 and MAC address. So MAC address mapped with the destination host IP address is not exactly of the end host device. MAC address, if you see the MAC address here, is exactly the same MAC address mapped with the IP 12.0.0.2, and 12.0.0.2 is R2 interface MAC address, right? So proxy ARP is enabled, so R2 must have like replied to our broadcast with his own MAC address, and you can verify from here also. But again, it's not very good practice, right? Why? Because let us assume there are like 200, 500, 300 host devices connected to the segment. So every time R1 will send the ARP broadcast message, who is 172.16.0.3, who is 172.16.0.4, 5, 6, 7, 8, 9 and so, right? And every time R2 will respond with its own MAC address. Too many entries here in the ARP cache table, right? So better to change the routing, not going this way. And how we can change the routing? So just get rid of this root 172.16.0.0. I'm sorry, 255.255.255.0 F0/1 and create route here 172.16.0.0 255.255.0.0, and here if you mention the IP and then question mark, right? So here like we find next hop IP address also, right? So now if you look at the routing table, perfect, right? Destination reachable via this next hop IP and next hop IP is reachable via this interface. Recursion is not required, no more recursion, right? We can see both. So, and in interior gateway protocols like OSPF, ESERP, RIP protocol, by default we see like both next hop IP and exit interface. In BGP we always see only the next hop IP address. So I hope you understand like routing basics, routing principle. So routing basic knowledge is really very, very important either like in networking or network security. So at least you should be familiar with the whole process, right? How it all happens, because routing is not all about creating a static or dynamic route only. We would have to ensure like all three steps are successful, not only step number 1 or 2. And in most of the cases, problem would be either with the step number 1, that is finding out longest matching route or exit interface, or maybe step number 3, that is encapsulation, because switching is the internal process, IP forwarding, IP routing, moving packets between two interfaces of the device is internal process, IP forwarding, right? So if IP forwarding or IP routing is enabled, then yes, packet will switch or move between interfaces. So we don't have to do anything for that. So that's all like about routing basics. And next I will explain about switching in detail, right? Because like there's a lot of confusion in switching. I mean mainly about the interface type, access port, routed port, right? SVI, switch virtual interface. So difference between virtual and physical interface. Then further in switch port also, like these access port and trunk port. In trunk also whether DTP or manual trunk negotiation. So too many things to discuss in switching part. So I will try to explain everything, right, about physical and virtual interfaces. Further, like physical interfaces could be the layer 2 or layer 3. Layer 2 means switch port, layer 3 means routed port. And then in layer 2 further access and trunk port. In trunk again like manual or DTP negotiation. Then in DTP like there are multiple modes. So I will try to explain everything in single session, right?